Okay, so I wanted to do this little video about tone stack that I made. You know, like the guitar and bass, they have these tone stacks, like the Fender and Marshall tone stack, and there's a wonderful program, the Duncan's tone stack calculator. Let me kind of show you that. Probably a lot of people have seen this before, but like there's bass, treble, mid. I'm going to change this to a low impedance source, just put like 1 ohm and make this arbitrarily high. Let's see there, 10 meg. So this is kind of what you're looking at here. You can see one of the problems, if it's not necessarily a problem, but it's a potential issue with these types of circuits is when the mid control is all the way up, there's still a big dip in the mid. Now this is actually very good for guitar, I think, because I think a straight signal with a guitar generally sounds pretty bad, and I really like this obligatory mid-range dip. So here's sort of this is an example. This is a Marshall tone stack. There's Fenders very similar. There's different types, but these are passive components, just resistors, capacitors. Now, if you look at this Marshall tone stack, you basically, of course, you've got bass, mid, and treble controls, and you've got 4 parts here. So what I wanted to do, now another thing to notice too is the input impedance. It's kind of depends on the frequency, but there's a range here from like 30 to 200 or so, and so there's some problems with the tone stacks and how you use them, but I mean they are good, and I use them all the time. I mean, there's nothing wrong with them. Just saying each circuit has its own strengths and weaknesses, and this loss is a weakness to me, and probably the impedance of these things. And plus, it's not very sharp either. This is about as sharp as you can get it, honestly. That depends on the ratio of these 2 resistors and so forth, but we won't get into that. So I started thinking, well, I'd like to make a different tone stack, and I don't want to make something that's worse. I mean, of course, that wouldn't make any sense, but so I started looking at inductors. Now, sometimes people say inductors, we don't like to use them because they're impractical. They have these images of, big windings and a transformer, and this stuff. And, actually, you can get, this is 0.1, but I'll rewrite it, is 100 millihenries. And let's just take a look here. I'm just going to go to eBay and put in 100 millihenry inductor. And let's see what we've got here. These aren't real common parts. I stock them because I fool around with stuff like this. If you look at this, you've got 100 millihenry, 10 pieces for about $7. Here's 10 for free shipping for $6. It's not that cost prohibitive. I mean, gosh, they're only 60 cents a piece, and you can see you can buy them in packs and stuff. So it's maybe a little bit of an unusual part, but it's not that unusual. So here's what I thought. This is basically, if you look at these 3 different parts here, I've got bass, mid, and treble, and I'm just gonna, just pull these down. Okay, this is a high pass filter. You've got basically a resistor and an inductor. Now this is a control to basically, when you crank this bass up really high, this whole thing gets ignored. I mean, think of it, if this was infinite, this would just be hanging there. It would do nothing. If it's 0, of course, it's in full effect. So, you can look at the results of this. You can see the bass going up and down there. And I won't go through each one of these. Now I'll talk about the next one for a minute. This is a little mid control. You've got a capacitor and an inductor. So this is what you call an RLC circuit. You've got the resistor, capacitor, and inductor, and that creates there's like a resonance between the capacitor and inductor. I'm not really going to get into all that because it's not really the purpose of this. I mean, you can look up tutorials and things on RLC filters and notch filters and so forth, but I'm just kind of showing. Now here's you can see this is a mid control. This is with the mid down and the mid up. And I'm using kind of arbitrarily large resistors. They're 100K, and that's too much, but it's just for the purposes of showing this on on the simulator. Now something else here. Let's look at this. See, these all have series resistance. The ones I showed you on eBay have usually around a resistance of about 200 ohms. So you can see the difference. Remember how sharp that was a minute ago? That's this. You can see it's much more. It changes the properties of it, obviously, quite a bit. So, okay, I'm going to change these also to be more realistic. Okay, and you may recognize this. I mean, this is sort of even like a guitar. Tone controls usually like this. There's sort of the guitar pickup is like 10K or so. Then there's some resistor, or I'm sorry, some capacitor there, like a treble bleed capacitor, and then you sort of force that out with the treble control, and you'll see this is. So this is, maybe I'm going into this a little bit too much, but you can see the treble here, and they kind of overlap these ones because I have the same capacitor here and the same inductor, but you can change the values of the cutoff frequencies by altering these capacitors and so forth, or now this here mainly it controls with this here mid control. It basically kind of controls the width of it a little bit, and the sharpness. It's complicated. I think there's a good website where you can do an RLC notch filter calculation. You can just Google it. I mean, there may be more than one, but you can put in different parameters and watch the Bodie plot and things like that. But you could even make, like, I've built actually a few EQs like this where you've got different mid bands and so forth. But anyways, here's kind of all of them together. You can see you've got, sometimes you get these weird little resonances too because of the phase shifting with the inductors, but you can see bass, you can see all the different types of plots. I'm going to take the phase out here for a minute just to kind of look at that. It's kind of usable, So let me change this out. So this got me thinking. Now this is pretty cool. I mean, it does have the benefit that when you turn up these resistors all the way, you get a pretty flat area there. And let's kind of zoom in on that. You can see this is kind of flat. It's about there's a decibel loss. Some of that loss is basically due to this resistor being 1K and we've got a 10K load. So that's where you're seeing that loss from. If this was a bigger load, that you'd have less than a decibel loss. The reason I picked those values is because I'm kind of saying, well, maybe you're using like a phone or something that you would hook headphones up to, and that's usually has a pretty low impedance, and then you can run that into 1K, and then most auxiliary inputs or amps or things like that have 10K or above. So this is kind of actually realistic. These obviously, this whole circuit can be done with very common parts. Now I think you'd want to use log pots, and I don't think you need quite 100K, but one of the reasons I wanted to show this video is because I thought, well, can I make something very, very simple, like even more simple than this? I mean, because you do have a lot of parts here. It's passive. It's flat at the top when the controls are up, so that's very neat. It has different advantages over the prior tone stack I showed you. I mean, it's sort of doesn't have this wide input impedance variation. It has more parts. The other one had 4, and this has 1, 2, 3. Well, it's got 5, so it's got one more part. If that really matters that much, but these are kind of uncommon too, and you've got 2 inductors in one circuit. So I thought, well, can I combine these some way? And basically, I don't know exactly how I figured this out. It's not that complicated, but I just looked at it as like maybe a puzzle with pieces, and I took this mid and I put it in between these two, which is fine because it's a series thing. It's a series circuit. And then, just sort of figuring things out here, you can basically, if you put a control from here to here, you bypass the treble control, and the mid, and you're only left with bass. And likewise, if you bypass the inductor, which is in control of the bass and the mid, then you have a treble control. And of course, if you turn this down, it lets this signal go through. For the notch filter, you turn it up, it doesn't allow anything. So, it's kind of, if I kind of do it a little differently. Well, tell you what. I think you can see here, if you bypass this totally, you're just left with one resistor. If you bypass this totally and these two are up, you just have basically a bass control or high pass filter, and you can kind of go through this. I'm not going to go into every scenario here. Now you probably could make another arrangement with maybe the capacitor down there and the inductor up there, but I think the mid has to be in the middle. I don't know how else you could do it. So let's take a look at this. See, this doesn't have any resistance, but we'll just kind of show you what this looks like. Now this has 1, 2, 3, 4 parts other than the controls. Of course, I mean those are parts too, but it's just the way I'm choosing to look at it. So let's take a look at there. Now here we go. So I'm going to remove these phases just because they're in the way. So yeah, you got the mid control going up and down. There's bass, there's treble, and so forth. And there's the flatness, which is better for like hi-fi or maybe even bass guitar, depending on what your opinion is on that. Now let's put some series resistance here to make it realistic. Okay, so we've got there we go. So yeah, it's just kind of cool. I mean, it works, Now you can't really, well, let's see here. So this has about 500 hertz mid-range control. That's fine. I mean, you can change basically what's happening here is, and this is a little bit different than other circuits because, see, here's the roll off on the bass, right? Yeah, going just like this, and this is the mid. So basically the cutoff frequency of the mid range here, or the central frequency rather, is 510, around 500 hertz. And the actual bass control, the cutoff frequency of that is like, above 500. And that's unusual because normally, at least for me, well, I guess it's not totally unusual, but usually I'll put a mid filter, at 1K or wherever, and then the bass control is less than 1K cutoff frequency or around the same, and the treble, here the treble cutoff frequency is lower than the mid frequency. So it is kind of an unusual circuit, but it does work okay. I mean, it's just different. It has, it has some value to it because of its simplicity and because I find it interesting. Now, of course, if you were to use this in real life, like maybe you'd probably, for good form, you'd put like a capacitor here. I'll just use 10U. So, sometimes for these simple circuits, I know you're not supposed to do this, but I'll put a multi-layered ceramic capacitor there just because they're so hardy, compared to an electrolytic capacitor, they go bad sometimes. They've only got so many hours. So, in a real life situation, I would put a capacitor here and there, although it may not be necessary. Let's see what that looks like. Yeah, that's fine. And you can see a little bit of a loss. I think this is because I'm only using a 10. These should be, especially this one, should be a little bit bigger there, and you're seeing a little bit of bass loss. But I would still build it this way because I like the fact, I don't usually, if I can get by with a 10 microfarad capacitor, that's what I'm going to use, because you can get tantalums that way. You can use a multi-layer ceramic, which I do sometimes, and I know, anyways, that's a separate discussion. And, you could just use electrolytics, but once you get above 10, then your choices are a little bit more limited. So this is actually, I would say, a usable tone stack circuit. It's got, other than the controls, and of course, I kind of not counting these when I compare it to like a Marshall or Fender tone stack, because they're going to have usually capacitor, coupling capacitors on either side also. I mean, it depends on what's preceding it and what goes after the circuits. I can't say that always, but so I'm just kind of counting these 1, 2, 3, and this is like I said, fairly common part. So hope you enjoyed looking at this. Like I said, it's just when you look at circuits, I want to show this tone stack calculator again. Here's Marshall, Fender, Vox. Let me see if I can make this a little bit bigger. Yeah, well, the circuit isn't bigger here, but anyways, Marshall, Fender, Vox, James, E-Series, Bench, Big Muff. I should do a video on this because I think there are some easy ways to explain it. Anyways, high watt, I think that's a new addition. Anyhow, you can see this is, pretty simple. Compared to the other ones, it is flat. A lot of the other ones aren't that flat, and so hope you enjoyed looking at this. It's just something I just kind of created on my own. I don't know if anybody's ever done it before, but if they did, I've never seen it before. And so hope you enjoyed looking at this. Now, one reason I am also showing this video is because somebody wanted me to do a bass guitar preamp. And I kind of use this circuit as the base for it. Now, only that is a very interesting circuit, I think, because I use a transistor gyrator. And instead of the inductor, I use a simulated transistor inductor called a gyrator, and I think it's really cool. I don't see many videos on it, and I use it in this context here to make a parametric equalizer for a guitar with just a few transistors. So I wanted to put this one out there first so like people would understand what I was doing to build the bass guitar preamp. So I hope you enjoyed watching this. And I want to say one other thing. I know I'm kind of long-winded today, but the guy that developed this, his name is Dave Signa, and I just want to thank him for that. I went to school with Dave for years in the physics department at Ohio University, and he's a great guy. I don't know whatever happened to him. I hope he's still alive. I don't see him. I don't see almost any internet presence of him at all. So he's either very reclusive or, Maybe he's working for the government, who knows. But he's into a lot of tube stuff. I hope he's doing well, and thank you, Dave, for working on this. Thank you very much. Oh, and I wanted to say one other thing. Obviously, these are too high. I would say something like 10K log or something would be the best for here. And if you can't use a log, you could even use like 5K, but you're going to have some loss there. So I switched these to 5K, and let's just see what that looks like. Yeah, so this is flat, but there's some loss here. This doesn't quite come up all the way. Yeah, it's a fair amount of loss, 2 decibels, 3 decibels. So that's probably, hard to say. Maybe like 20K log would be good. I think you're better off with the log pot. Now, on the other hand, like I always try and substitute linear stuff when I can. I know maybe it's bad form, but I do it just because I've got shelves full of linear stuff. And let's see what 20 is. Yeah, okay, we've got about 1.5 decibel loss, almost 2 there. That's probably not bad. I mean, for a passive EQ. You know, I don't know. You just kind of have to experiment with it. I mean, it's still flat, but probably something like a 20K log would be good. You know, 1 decibel loss is not insignificant, but it may not make a difference many times. I mean, if you're going from like a phone or something to an auxiliary thing, it's not going to matter really. But you know, for professional stuff, maybe you want different. So I would say, you know, I don't know. You could just try different pots out. I mean, just kind of do it by ear or whatever. But all right, thank you. Okay, I wanted to mention one thing. I mentioned there's a website. This is a very, very good one. If you look up RLC band stop filter, you can see this is kind of the mid control. You've got a resistor, the inductor, and capacitor. They're in a different order, I think, on mine. But anyways, here's a couple things to note. The frequency, like if you want to change the frequency of the mid range, usually I would change the capacitor and the inductor. You know, I don't stock zillions of different values or anything. Usually that's a part that you'd usually more easily change the frequency with capacitor. You could even put like multiple bands for like a graphic EQ. But anyways, the resistance has nothing to do with the frequency. So what does the resistance do? Well, you know, these are complicated equations, and I can just tell you, just from experimenting and so forth, that if the resistance is lower, the notch depth will be lower, and if it's higher, the notch depth will go higher, or I'm sorry, the notch will go lower. So if you push this up, the notch starts going low. But I think the Q, at least from my experience, I believe I remember it starts getting wider also. So there's kind of this widening of the Q, you know, like the whole. Let's just put something else in. I'll put a 10K there, and let's look at this. See, this is way wider mid-range now, and it's much lower too. Look, there's 36 decibel loss and so forth. Now this, you know, let me just make this large for now, just so we don't have to worry about loading effects. So yeah, you can see this is totally changed. It's like way deeper, and way wider. So the Q is worse and the depth is worse. I believe the Q is worse. Let's see, let's make it 100. You can see that it's just barely there. It's not much of a dip there. So I'm going to zoom in on that for a second. And see, we've only got like a 3 decibel, loss there. Of course, this is a loading effect because I didn't change this capacitor there. That needs to be higher to bring that back up. You can see that the dip is different. I think the actual Q is also affected by the intrinsic resistance of the inductor, because when you pull this down, you're going to see that sharp. It's much sharper and it goes lower. So it's sort of all these factors are, but the one thing you're going to want to know is how to calculate the frequencies of these bands and so forth. And basically, I would probably stock up. This is about the highest inductor that you can get that's sort of common and cheap. Once you go above that, I mean, I think there are some 200s I've seen out there. But anyways, so you're going to want to change the frequencies with this. And I wanted to show you, definitely wanted to show you the frequency formula and sort of let you know how this R works. I built a preamp before, and I put a pot here, and I sort of I already knew the frequency, and I sort of adjusted this. It was like a trim pot to sort of get it sounding how I wanted, and that's one way you can work with these types of circuits, because sometimes it's just do it by ear. But anyways, it's a little bit more. I wanted to show you those equations. Thanks for watching.